Today we're going to be starting with electrochemistry, okay, and in electrochemistry first we're going to learn about electrochemical cells. Okay, electrochemical cells. Now when we talk about electrochemical cells, there's two broad categories that we talk about. The first type of electrochemical cell that we learned about is what we call a voltaic cell. Okay, a voltaic cell, also known as a galvanic cell. Now in voltaic cells or galvanic cells, okay, chemical potential energy is converted into electrical energy. It's converted into electrical energy. Right? So we can say that voltaic cells or galvanic cells generate electricity. Okay, they generate electricity. Right, and then that electricity can be used to do work. Okay, that electricity can be used to do work. The other types of cells that we talk about are called electrolytic cells. Electrolytic cells. Now, in electrolytic cells, we have the reverse. Electrical energy is converted into chemical potential energy. So electrolytic cells consume electricity. Electrolytic cells consume electricity. So when we talk about voltaic or galvanic cells, right, the electromotive force, that's the voltage of the cell, the EMF, is positive, okay, because they generate electricity. And then electrolytic cells, because they consume electricity, the EMF for that cell is negative, right? The EMF is less than 0. Okay, that's the electromotive force. For example, the battery cells that we use in our remote controls, right? Those are voltaic cells, right? They contain voltaic cells. They're able to generate electricity, right? The battery contains chemicals. We put that, for example, in our controller, right? In our TV remote, for example, and then, right, they generate electricity, and we can use that electricity to do work. Similarly, if we have a battery in our laptops, right, they generate electricity. We can use that electricity to use our laptops, right? So we can use that electricity to do work. When the laptop runs out of battery, right, when it runs out of battery, then when we recharge that battery, when it's recharging, the battery is behaving as an electrolytic cell. In that case, right, the battery is consuming electricity, and that consumption of electricity results in the recharging of the battery. Okay, so some cells, such as battery cells in remotes, your standard battery cells, right, the non-rechargeable ones are voltaic cells, for example, right, and then something like rechargeable batteries, when you're consuming the electricity that they're generating, they're behaving as voltaic cells, and when you're recharging them, they're consuming electricity, so they are electrolytic cells. We're going to start with voltaic cells, okay, also known as galvanic cells. So before we get into what voltaic cells are, okay, we're going to look at redox equilibria. Okay, so let's say that I have a beaker in which, okay, I have a 1 mole per dm cube. Okay, I have a 1 mole per dm cube Zn2 plus solution. 1 mole per dm cube Zn2 plus solution. So I can use something like zinc sulfate, for example, to make that solution. Right, I can use something like zinc sulfate to make that solution. And what I've done here is in this solution, I have a strip of zinc metal that I've submerged in this solution. Okay, so here I have a strip of zinc metal. Okay, so this is Zn metal. So in this case, we have an equilibrium between zinc metal and zinc ions. Okay, so we have the following equilibrium. Okay, we have the following equilibrium. We have Zn2 plus 2 electrons, right, makes Zn, right? What we're saying is that over here, the zinc metal, right, and the zinc 2 plus ions that are present in solution, right? So what's happening is that zinc metal is dissolving to form zinc 2 plus ions, and at the same time, the Zn2 plus ions are are gaining electrons to form zinc metal. Okay, so this is an example of what we call a redox equilibrium. Okay, this is a redox equilibrium. Redox equilibrium. Right, so we have this redox equilibrium in this solution. Okay, we have this redox equilibrium here. So now let's say that I have another beaker. Okay, and in this beaker, instead of zinc, instead of zinc solution, I have a copper 2 plus solution. Okay, so let's say I have a 1 mole per dm cube, 1 mole per dm cube, copper 2 plus solution. So 1 mole per dm cube, copper 2 plus solution. Okay. So I can use something like copper 2 sulfate, for example. So here I have 1 mole per dm cube copper 2 plus solution, and here I have a strip of copper metal. I have a strip of copper metal that I have submerged in the solution. Okay, I have a strip of copper metal that I have submerged in the solution. Okay, so here I have copper metal. So over here I can say I have the following redox equilibrium, right? I have copper 2 plus 2 electrons, right, in equilibrium with copper, right? So I have an equilibrium between copper 2 plus ions and copper metal, right? So what we're saying is that the metal is losing electrons and dissolving in solution to form copper 2 plus ions, and at the same rate we have copper 2 plus ions depositing, right, or gaining electrons to form copper metal. So I have a redox equilibrium in this beaker and I have a redox equilibrium in this beaker. Now let's say that I take this strip of zinc metal, okay, and this strip of copper metal, and I connect the two using a wire. Okay, so I connect the strip of zinc metal to the strip of the copper metal using a wire. So over here, initially in each of the beakers we had redox equilibria. But once we connect the wire, we know that the two metals are conductive surfaces, and the wire can also conduct electricity, right? So now the electrons are free to move. And from our previous understanding or previous knowledge, we know that zinc is the more reactive metal, right? Zinc is more reactive than copper, so zinc loses electrons more readily, right? Whereas copper is not as reactive. So here what will happen is that because zinc is a more reactive metal, okay, the electrons will flow from zinc towards from the zinc electrode towards the copper electrode. So here we have a flow of electrons. From the zinc electrode to the copper electrode. Basically, the electrons are flowing from the more reactive metal to the less reactive metal. So then what we can say here, the first thing we can say is that we know that zinc is a better reducing agent. Than copper. Zinc is a better reducing agent than copper. In other words, zinc loses electrons more readily than copper does. We can also say that copper 2 plus is a better oxidizing agent. Copper 2 plus is a better oxidizing agent than Zn2 plus. So what that means over here, of course, is that zinc loses electrons more readily than copper, right? It undergoes oxidation more readily, so it's a better reducing agent than copper, whereas copper 2 plus accepts electrons more readily than zinc 2 plus. So therefore, copper 2 plus is a better oxidizing agent than Zn2 plus. It undergoes reduction more readily than Zn2 plus ions do. Of course, zinc is the more reactive metal, then this equilibrium, initially before the wire was connected, this equilibrium would lie further to the left, right? Which meant in this case the backward reaction was more favored than the forward reaction, right? Relative to the copper, where this equilibrium would have lied further to the right. So here the forward reaction was favored more than the backward reaction, right? So we can say that you have the better reducing agent here amongst the two metals in zinc, and you have the better oxidizing agent here in copper 2 plus, right, amongst the two ions. What I can say over here is that zinc is losing electrons, right, and then the copper 2 plus is gaining electrons. So electrons are flowing from zinc to copper, right? So the half equation that we have is zinc is losing electrons, right? And then copper 2 plus is gaining electrons to form copper metal. As the electrons flow from the zinc to the copper electrode, right? The electrons are leaving the zinc electrode. So we can say that this equilibrium is moving further and further to the left, right? So the reaction that's taking place at this electrode is zinc being converted to form Zn2 plus and releasing electrons. And then here this electrons are being accepted at this electrode, right? Electrons are being accepted at this electrode. So we have electrons coming in, that increases the number of electrons, and then this equilibrium is shifting to the right. So we have this half equation, right, for this electrode. And of course, we want to measure the potential difference. Here. We can use a voltmeter, right? So here we have a voltmeter, right? So this voltmeter can be used to measure the potential difference. Now what happens over here is that over time, right, as this equilibrium is essentially keeps on shifting to the left, we have this reaction taking place here, right? What happens over time is that the concentration of Zn2 plus in the solution begins to increase. Concentration of Zn2 plus in the solution begins to increase. What does that do to the charge of the solution? This solution become more positive over time because they're producing more and more Zn2 plus ions, right? The electrons are going from this electrode to this electrode. Over time, the concentration of Zn2 plus increases. We have the same amount of sulfate ions. They're essentially spectators here. So we can say that over time, the concentration of Zn2 plus increases, right? The concentration of Zn2 plus increases, and we can say that there is a buildup of excess positive charge in this solution. There is a buildup of excess positive charge in this solution. And of course, over time, as the electrons are flowing to the copper electrode, right, we know that copper 2 plus ions from the solution are depositing to form copper. So the concentration of copper 2 plus ions is decreasing over time, and the number of sulfate ions obviously is remaining constant. So since the concentration of the cations is decreasing, right, we have an excess of sulfate ions. So that means that we have a buildup of excess negative charge over time, right? We have a buildup of excess negative charge. Buildup of excess negative charge. Now, we want the electrons to flow from the zinc electrode to the copper electrode. And what we can see over here is that over time, right, as Zn2 plus ions accumulate here and copper 2 plus ions are consumed here, there's a buildup of excess positive charge in this electrolyte and a buildup of excess negative charge in this electrolyte. This buildup of charge will restrict the flow of electrons because electrons will not want to flow from a place that has excess positive charge, right, to a place that has excess negative charge. Electrons will want to stay with the excess positive charge rather than go towards the excess negative charge. So in order to prevent this buildup of excess charge, and in order to ensure that we have a flow of electrons, we use something known as a salt bridge. Okay, Okay, so this is a salt bridge. So this is called a salt bridge. Now, what exactly is a salt bridge? Okay, what exactly is a salt bridge? Now, a salt bridge can be made in two ways. Okay, the first way of making a salt bridge is simply by soaking a piece of filter paper. Okay, soaked in aqueous potassium nitrate. We don't have to use potassium nitrate. We can use some other electrolyte, but potassium nitrate is the most common choice. Or what we can have is cotton wool, right? You can have cotton wool, okay, or a glass tube containing cotton wool soaked in potassium nitrate. soaked in potassium nitrate. So we're saying is we can just take a piece of filter paper, right, soak it in potassium nitrate, and then we can just fold that filter paper and connect the two beakers. Or we can just take this U-shaped tube. Okay, we can take this U-shaped tube, right? There's a glass tube that contains cotton wool, soaked in potassium nitrate. Okay, so we have cotton wool in this glass tube, okay, in this glass U-shaped tube, and again we can use this U-shaped tube to connect the two. Beakers, right? So we can either just fold a piece of filter paper and connect the two solutions together, right, using the salt bridge, or we can use this glass shaped tube, okay, that contains your cotton wool soaked in your electrolyte. So now the way this prevents the buildup of excess charge, okay, is the following. Right, what we have here now, is, right, this salt bridge, it contains, or it consists of, or it's just a filter paper soaked in potassium nitrate aqueous, or it could be a glass shaped tube that contains cotton wool soaked in potassium nitrate. And what we said was that in this electrode, we had a buildup of excess positive charge due to the accumulation of zinc ions, right? And that excess positive charge can be countered, or that buildup can be prevented by the salt bridge, because the nitrate ions from the salt bridge, which are negatively charged, will flow from the salt bridge into the solution, okay, and they'll prevent the buildup of excess positive charge. Similarly, in the copper electrode, since copper 2 plus ions were being consumed, we had a buildup of excess negative charge. And in order to prevent that, right, what we can do is, by using the salt bridge, we know that potassium ions, which are positively charged, will flow from the salt bridge into this solution, right? So this will counter the buildup of excess negative charge. We can say that using the salt bridge prevents the buildup of charge. Okay, that using the salt bridge prevents the buildup of charge. So we can say that the salt bridge prevents the buildup of excess charge. The next question that we have is, which of these two electrodes is the cathode and which of these two electrodes is the anode? So reduction occurs at the cathode. Okay, or reduction takes place at the cathode. Reduction takes place at the cathode, and oxidation takes place at the anode. Okay, oxidation takes place at the anode. Oxidation takes place at the anode. So here we know that zinc is undergoing oxidation, right? It's the reducing agent. So the zinc electrode is the anode, right? That's your zinc electrode. And the copper electrode is the cathode, right? That's where reduction is taking place, right? We have gain of electrons taking place at the cathode, right? So that is the copper electrode. And of course, in this cell, electrons will flow from the negative terminal to the positive terminal, right? So here, this is the negative terminal of the cell, and this is the positive terminal of the cell, right? Electrons are flowing from zinc to copper, right? So we're losing electrons in zinc. Oxidation is taking place, that's the anode, right? We're accepting electrons at the copper electrode, so that is the cathode, right? Because reduction is taking place, gain of electrons, and since electrons are flowing from zinc to copper, this is the negative terminal and this is the positive terminal. So here we can say that the zinc electrode is our anode, and then the copper electrode is our cathode, right? So this is our half equation. This is our half equation for the anode, right? This is the reaction taking place at the anode, right? And this is the half equation for the cathode, right? So the half equation for the anode will show oxidation, the half equation for the cathode will show reduction, and therefore the overall equation for this cell. Now in order to construct the overall equation, we have to ensure that the electrons are balanced, right? In this case, the electrons are balanced, right? So we can just add up the two equations and we get the overall equation for the cell, right? So this is Zn plus Cu2 plus gives us Cu plus Zn2 plus. So this is the overall equation for the cell. Okay, this is the overall equation. So in this reaction, we can say that zinc is the reducing agent, right? In this reaction, we can say zinc is the reducing agent and copper 2 plus is the oxidizing agent, right? Zinc is undergoing oxidation, it's a reducing agent, and copper 2 plus is undergoing reduction, so therefore it is the oxidizing agent. So now let's answer the following question, right? Why is the salt bridge necessary? Why is the salt bridge necessary? The salt bridge is necessary because it prevents the buildup of charge, right? Prevents the buildup of charge. But in the example that we saw, if we didn't have a salt bridge, we'd have positive charge build up at the anode, right? And we'd have had negative charge build up at the cathode, right? Negative charge at the cathode. So what the salt bridge does is it prevents that buildup of charge. Okay, so the function of the salt bridge is to prevent the buildup of charge, and by preventing the buildup of charge, it ensures the flow of electrons, and therefore we can say that it completes the circuit. Okay, it completes the circuit. Okay. So it completes the circuit. Okay, again, in order for the circuit to be complete, electrons have to be able to flow, right? And they're unable to flow due to the buildup of charge. But if we have a salt bridge, right, it'll prevent that buildup of charge, and therefore it'll complete the circuit. Now the reason we use potassium nitrate is because all potassium salts are soluble and all nitrate salts are soluble, right? So nitrate is going here, doesn't matter what cation is present here, nitrate will not form a precipitate with that cation. Similarly, if potassium is going here, right, towards the cathode, you know that no matter what anion is present, potassium will not form a precipitate, okay? So that's why potassium nitrate is the most common choice, okay? That's why potassium nitrate is the most common choice. Okay, so potassium nitrate is used, is the most common choice, okay, because all potassium salts are soluble, all potassium salts and all nitrate salts are soluble. The next thing I want to do here is I want to define the standard cell potential. Standard cell potential. The symbol that we use for this is E naught, okay, with subscript cell. So over here, E stands for electromotive force, right? That's the voltage, and then theta over here just means standard conditions. Standard cell potential is the potential difference, okay, the potential difference between the cathode and the anode of a cell, okay, cathode and anode of a cell at 298 Kelvin, 1 atmospheric pressure, using 1 mole per dm cube solutions, using 1 mole per dm cube solutions, right? These are your standard conditions, okay? For cells, you have to ensure standard conditions are 298 Kelvin, 1 atmospheric pressure, and 1 mole per dm cube solutions, right? The reason I'm saying this is because if we vary the concentration, of, in this case, for example, Zn2 plus or copper 2 plus, we would affect the direction of the equilibrium and therefore affect the value of the potential difference, right? So therefore, for standardized conditions, we have to use 1 mole per dm cube solutions, okay, for our electrolyte, okay? Obviously, the potential difference between the cathode and the anode is simply the voltage, right? So we can say that the standard cell potential is simply the voltage of a cell at 298 Kelvin, 1 atmospheric pressure, using 1 mole per decimeter cube solutions, right? Because the voltage is the potential difference between the cathode and the anode. So in this particular example, right, that we saw, the E naught of the cell, right, the E naught of the cell was 1.10 volts, okay? And we'll also learn how we can determine the value of the EMF or the voltage of the cell as well. Okay, but in this case, I'm just letting you know that the EMF of this cell, was 1.10 volts. Okay, so the units for this are volts. One last thing I want to mention here is that this voltaic cell is made up of two half cells. Okay, we have two half cells, right? Here we have, this is our zinc half cell, okay, and then this is our copper half cell. Okay, so we have two half cells here. We have a Zn/Zn2 plus half cell, right? That's the half cell. Where zinc is undergoing oxidation, right? That's your zinc electrode, right? That's your Zn2 plus half cell, and then we have the copper 2 plus slash copper half cell, right? That's your copper electrode. Right? Where copper 2 plus is undergoing reduction to form copper. Now two half cells will make up a full cell. Okay, so this cell is made up of these two half cells. Okay, this cell is made up of these two half cells. And we have this half cell, and we have this half cell. What we also observe here, okay, that tells us that zinc is more reactive than copper is the fact that the mass of the zinc electrode decreases because over time the zinc metal is converted into zinc ions. So the mass of the anode decreases, whereas at the cathode we know that copper 2 plus ions gain electrons to form copper, right? So we have deposition of copper at the cathode, and therefore the mass of the cathode increases. And over time we also see that the blue solution, right, of copper 2 sulfate would fade, right, because copper 2 plus ions over time will react to form copper.